Welcome back to the Explainer. Today, we're taking a bit of a technological time warp. We're looking at how fundamental 19th century physics equations haven't just survived the test of time. They've actually become the invisible forces literally powering today's cutting-edge AI and smart factories.
Here's our quick roadmap for today. We'll start with the smart factory revolution, then look at the physics powering the future, break down sensors and actuators, explore AI and wireless innovations, and finally wrap up with the automation age benefits.
Okay, let's jump right into Section 1, the smart factory revolution, and how we're integrating IoT and electromagnetism. To really map out modern industrial automation, the classic human body metaphor is honestly still one of the best ways to picture it. Think of the sensors as the nervous system. They're out there detecting these tiny micro-variations in heat, proximity, or speed. Then you have the actuators acting as the muscles, doing the heavy lifting and making those super precise mechanical movements. And tying it all together, AI and the Internet of Things act as the brain. But, in a modern factory setting, this isn't just basic stimulus and response. It's a highly sophisticated loop. We're talking about edge computing processing nervous system signals in literally milliseconds, which lets the brain perfectly orchestrate those muscles for real-time autonomous optimization. It's wild.
Let's keep moving to Section 2, Physics Powering the Future, the 19th century equations behind all this modern tech.
At the absolute root of that industrial nervous system is Faraday's law. Simply put, it establishes that a changing magnetic flux induces voltage in a conductor. In an advanced factory context, this equation is the exact mechanism that allows an assembly line to actually feel its environment. When a high-speed metallic component zips past a proximity sensor, it rapidly disrupts the local magnetic field and generates a microvoltage. That tiny, almost imperceptible electrical jolt is the exact signal the AI brain relies on to track components moving at thousands of units per minute. Next up, we have the Ampere-Maxwell law. Now, if Faraday's law allows the factory to feel, the Ampere-Maxwell law allows it to act. By inducing magnetic fields through electric currents, AI algorithms can instantly translate digital commands into high-torque physical motion. This is the core principle driving modern robotics. It grants heavy-duty actuators the power to push, pull, and articulate with incredible precision and force. It's essentially the process of taking digital code and materializing it into real physical action.
That perfectly sets up Section 3, Sensors and Actuators Explained, or as we call them, the factory's nervous system and muscles.
Understanding that symbiotic loop really clarifies their distinct roles in Industry 4.0. Things like inductive proximity and Hall effect sensors leverage Faraday's principle to detect environmental shifts, turning physical magnetic changes into actionable electrical data. On the flip side, electromagnetic relays and solenoids do the exact opposite. They rely on the Ampere-Maxwell principle to convert that electrical energy back into hard mechanical force. Without sensors, the factory is totally blind, and without actuators, the factory is completely paralyzed. Together, they create this continuous, beautiful feedback loop that defines smart manufacturing.
Let's scale things up a bit for Section 4, AI and wireless innovations, looking at the latest advancements from 2021 to 2026.
Right now, traditional electromagnetic components are being radically decentralized and optimized. The integration of AI-enabled smart sensors, wireless industrial IoT, and highly intelligent electromagnetic actuators represents a massive evolution in how factories operate. We're essentially shifting away from rigid, reactive hardware setups into entirely proactive, smart ecosystems.
And each of these innovations acts as a vital, distinct upgrade. For instance, AI-enabled sensors don't just register machine vibration, they actively analyze the signature of that vibration to predict failure patterns before a breakdown even happens. To put that into perspective, implementing this kind of predictive AI can slash unplanned factory downtime by up to 50%. That is a total game changer. Meanwhile, wireless industrial IoT cuts the physical cords, dramatically lowering deployment costs and letting engineers monitor systems remotely from anywhere in the world. And intelligent actuators, they now integrate real-time feedback loops directly into the hardware itself. This secures the microscopic precision you need to manufacture things like delicate modern electronics, all while constantly optimizing energy use.
I think Nabiha, an engineering student at UTHM, whose notes actually inspired today's explainer, sums it up perfectly. Quote, "Sensors and actuators are becoming more intelligent through the integration of artificial intelligence and the Internet of Things." It really highlights a fascinating reality of modern engineering, doesn't it? These ancient textbook equations are seamlessly blending with the absolute cutting edge of digital intelligence.
Which brings us to our final part, Section 5, the automation age benefits, and why this tech actually matters.
Implementing all this electromagnetic technology generates a cascading series of incredibly tangible real-world benefits. Because AI continuously predicts failure points before they ever happen, we're seeing a drastic reduction in maintenance costs and unplanned shutdowns. And of course, that operational stability inherently skyrockets overall productivity. At the same time, relying on intelligent actuators for hazardous or super repetitive tasks gets human workers out of dangerous environments, which vastly improves workplace safety. Tie all of this together with real-time monitoring and high-precision control, and the inevitable outcome is a significantly higher quality product for the end consumer. It's a win all around.
Now, because IoT and electromagnetic technologies are evolving so rapidly, just relying on static knowledge isn't going to cut it anymore. Continuous education has basically become a professional requirement. As highlighted in BIHA's notes, maintaining a lifelong learning plan, whether that means tracking IEEE research journals for the latest sensor tech or jumping into specialized webinars and online courses, is absolutely critical. In the fast-paced ecosystem of Industry 4.0, staying actively updated is literally the only way to ensure your technical expertise doesn't become completely obsolete.
We've seen how equations written by Faraday and Maxwell well over a century ago serve as the literal nerves and muscles of today's AI-driven smart factories. So I'll leave you with this final thought to ponder as you commit to your own lifelong learning in this space. If 19th century math is driving today's smart factories, what completely new physics will be building the factories of tomorrow on? Thanks so much for joining me for this explainer, and keep learning.